Can you hear me at the back? Am I yelling loud enough? Cool. Hello, welcome to this talk on Hans' introduction to quantisation, where I'm basically going to go over weights in neural networks and how you can utilise quantisation as a technique to run that on constrained compute, such as edge nodes or embedded devices, such as the little Raspberry Pi down there, which is a live demo. So let's hope the demo gods are kind to me today. This means of an introduction. I'm Ben. There you go, Ben Clark. I'm a DevOps contractor and have been for 15 odd years now, give or take. I tend to specialise in platform engineering and Python software development. For the past 6 years, though, I've also been doing an undergraduate degree specialising in the mathematics behind AI and ML. So I've got a nice crossover between nearly 2 decades of professional experience and a good theoretical underpinning in how all this AI gubbins actually works. So in preparation for this talk, there's only so much I can cover in the time that we have. So what I have been doing on my blog is basically going into these concepts in a lot more depth. So if you scan it there, you can get to my website. Equally, the talk I'm going to do today, if you've been to any of my other talks, a lot of them have been about ways of working and methodologies. This talk is a lot more of an in-depth tech dive. So you may have some questions afterwards that it takes your brain a bit of time to figure out. If that's the case, just my website links to my LinkedIn. You can send me a message there. You can email me. I'm happy to answer any questions you have after the fact. But before we head off today, just so you know sort of where we're going, I'm going to try and, before I get on to quantisation, I don't want to assume any prior knowledge in the room. So I'm going to try and give you, as much as I can in 20 minutes, a good foundational understanding of how AI and ML works, around how weights are utilised in neural networks, as well as how activations work, as well as MLPs. And then we'll go on to the concept of quantisation, both approaching it initially from one of its core use cases, which is in audio engineering, and then seeing how you can transcribe those concepts and principles through to AI and ML in order to run models on constrained resources. There will also be a Q&A at the end, but some of my demos are quite long, so you'll probably ask questions during them. I'm just going to kick this off. There you go. That is a live neural network running on 8 gigs of memory on the Raspberry Pi. Takes about 8 minutes to generate an answer, but considering it's got 7 billion parameters, I think that's okay. So without further ado, I've built an educated software for this workshop here. So we're going to try and present some of these ideas visually. We're going to give you some nice, pretty graphics, a bit of maths as well. And hopefully, if you're a bit like me, where you're more of a visual learner, should hopefully assist in actually sort of understanding this stuff and not just being very confused by it. So right at the start, if you haven't done sort of any technical deep dive on AI and ML, I'd recommend starting the perceptron. It was made way back in the 50s by Rosenblatt, and the fundamentals of it are still relevant today. The way that neural networks work have changed a lot, but the underlying mathematical theory from way back then still holds up. So it's a good place to start if you want to try and understand how AI and ML actually functions. At its core, can you all see that back? Cool. At its core, it just takes any number of inputs, which I've labelled as X here, multiplies them by some kind of weight, and summarizes all of them together, adds a bias, and then does a thing. And that thing will determine what the neural network does. The original perceptron is really, really basic. It uses what's called a step activation function. And so it's just 0, 0, 0. You reach the threshold, it's a 1. You can probably guess that's quite limited, but what it lets you do is binary classification. So if your data engineering principles are sound and you know that in your data set you can classify things as either class A or as class B, you can utilize a perceptron in order to do that. So we can see that in 2 dimensions, the way that might work is if all your data points are linearly separable, then a step function and the perceptron's job is just to draw a line through them. And all the stuff in class zeros on one side, all the stuff in class A is on another. If you push that up into 3 dimensions, is that feasible? Yeah, it is. It just becomes a hyperplane. It's just a fancy word for coloured lines in 3 dimensions, or planes, if there's any mathematicians who are going to lynch me in here. Neural networks tend to operate at a lot higher dimensions than this. So the network running there, I think it's about 7 billion or something ridiculous like that. Very, very difficult for humans to comprehend. Explainability, as Matt mentioned in his brilliant talk, is one of the problems of these networks, is trying to figure out what they do and why they do it. But I'll come on to that in a bit more detail in a bit. But fundamentally, all you need to understand, regardless of the number of inputs, just for the purposes of quantization, is any number of inputs, they get multiplied by weight, add them up, add a bias, a thing happens, yay, you have some kind of classification. A lot of data, if any of you are data engineers, you will know is not linearly separable. In an ideal world it would be, but it is not. And that led to a bit of a cooling down of AI and ML, sort of through the 60s and 70s, until we started to discover different ways we can mathematically separate out data into more than one data set. Now, this talk isn't on activation functions, so I'm not going to go over all of them, but I'll just focus on one just to sort of demonstrate the point. Regardless of that perceptron I saw earlier, it passes all of its inputs that are multiplied by weights with a bias into a step function. The step function just transforms it. If you look at a slightly more advanced one, like ReLU, you can see here that in 3 dimensions, rather than a sort of a step, it's more of a gradual gradient and a curve there. Or a classic one is a sigmoid, is a nice, pretty curve that looks nice on a big screen like this. But regardless of what you're doing with those inputs and how you're transforming them, ultimately the network depends upon getting some kind of input, multiplying it by weight, doing the thing. Now, a single perceptron, as you're probably aware, is not how neural networks operate these days. They are a lot larger. While the term multi-layer perceptron is a bit of a misnomer for what networks are, I'm going to use it anyway because it makes sense in your heads. You can see here what a slightly larger network may look like with let's just use a ReLU, for example. Really basic network. You get all your inputs, you whack them through to an input layer. The input layer all behaves like that perceptron I mentioned earlier, where it takes inputs, does something, outputs something, puts it through to one or more what's known as hidden layers in your network. And in modern neural nets, these can be extremely deep. So you can have many hidden layers. And by having activation functions that can classify or interact with nonlinear data, you can do really cool things like if I want to build a network to go, do I want to eat this cake, for example, right? Very hard, pressing, serious question. One neuron might be, is it chocolate? Another neuron might be, what's the shape of the cake? Another might be, well, how full am I? And then depending on which of these features I'm interested in, it may be the network discovers that I really like chocolate. And so the one here that discovers if it's a chocolate cake has a higher bias, so it gravitates towards outputting a higher number. And in the end, that means the network is more likely to say that I will eat the cake if it is chocolate. But ultimately, and fundamentally, all you need to understand for the purposes of quantization, which I'm about to go over, is just you take the inputs, you multiply them by weight, add a bias, and then just cascades and goes on and on and on and on. Large language models, although more accurately large reasoning models, their networks can be quite deep. They also utilize a function called transformers. There's a lot of complicated maths that goes behind that, but it still utilizes the same principles to behave the way it does. My screen's not working. There we go. However, as you're probably aware, things like ChatGPT or the latest version of Llama models are quite large. If you try to run them on your laptop or a Raspberry Pi down there, you're probably not going to have a lot of luck because you don't have enough RAM if you run it on the CPU. Or if, like me, you like to play video games and you tried to buy a GPU in the past 10 years, you will notice they've gotten really expensive. I'm not going to go over into the full details of why, but essentially you can see down here that what the maths transforms into is just a matrix multiplication. So your inputs being multiplied by weights just collapses into a matrix multiplication. GPUs are really, really good at that because that's how graphics work. And that is all the detail I'm going to give you because we're focusing on quantization. But if you want more, you can come up to talk to me afterwards. But this begs the question, okay, I want to run the latest model of a ML on my laptop or Raspberry Pi, or I have a company and I want to run a model, but I can't afford the GPU or the CPU to run the top shelf models in their current form. Is there a way I can perhaps reduce the compute required to run those models? And there is. So a long time ago, but not so long ago that it's not relevant, the same problem was faced by audio engineers. So if any of you know anything about audio engineering or remember anything from physics in school, you know sound travels in a... There we go, a wave. Look at that, you're awake, well done. And the thing about a wave is it's continuous. And a thing about a laptop and the digital format is it's not continuous, it's finite. You want to store things as a discrete vector of numbers. Wave isn't a discrete vector of numbers. And so when you're trying to record audio, you have to think, well, how do I do that? Because the real world is nice and pretty and there's a bunch of lines, but a computer is a bunch of ones and zeros. It can't model that. The solution that audio engineers came up with was something called quantization. Now, if there are audio engineers, don't lynch me. I'm only going over it in high depth because it's the prep for the ML stuff. But you can see here that if we use, for example, 2 bits to represent every sample of our sound wave here, that this continuous wave collapses into a data point here, here. And the error rate is quite high. So just using 2 bits, if you try to play 2-bit audio, it's going to sound quite janky unless it's, I guess, Super Mario World, in which case it's quite nice. But if you go up to, for example, what CD formats use, so CDs are typically, well, I guess they're not used anymore, but I'm going to pretend they are typically used in 16-bit depth. And you can see that if we utilize 16 bits to represent each and every sample point here, that our quantized version of the sound wave a lot more closely represents the actual sound wave itself. Now, it's not perfect. It's never going to fully map onto a continuous surface, but the error rate is quite low. As you can see, 1e minus 5, that's quite a low sort of fluctuation within that range. But more crucially, and for our audio engineers, they can correct me, because I do believe this is correct, but I may be wrong. Anything above 16 bits of depth, the error rate becomes so minuscule the human ear can't really comprehend it. So there's a space-time trade-off there, of space-time even trade-off, which is, yes, I could use more bits to represent my sound wave, and that may get me a more accurate representation of the real world, but does that really matter if the people who are utilising the results of that, i.e. people listening to Beyonce on Spotify, are going to actually be able to hear the errors? So if I'm using anything above 16, I'm essentially trading an idealized version of the sound wave for no discernible benefit to people, but it requires more space, it requires more computational power. The same concept here of taking a continuous series of values or taking a high fidelity data set and reducing it down to a low fidelity data set is something that data engineers do all the time, right? Like if you have a time series database, you may record your data in 0.5 millisecond increments, and then after a day you might collapse that through to 5 seconds, and after a month you might collapse that through to daily snapshots or whatnot. And the same way that we can quantize the sound wave by utilizing a certain bit depth, we can do the same with weights in the model. So you just see there, by the way, although you might not if you're at the back, the Raspberry Pi has just done an answer. I will keep this plugged in, so after the talk, feel free to come up and ask it questions. It does take 8 minutes, so just bear with it. It is actually no, remind me to talk about testing afterwards. It plugs into Matt's talk, but I want to do it afterwards once I've covered mine. But I have a good testing thing to tell you about that. You can see an original weight distribution here. Most models these days utilise 32-bit floating points for their weights. So the model that's based on is called Wizard LM7B. It uses 7 billion parameters. It's a llama derivative, though I may be incorrect. I always mix them up in my head. But it will originally utilise 32 bits to represent every individual weight. If you remember back in that diagram I showed you earlier, it's really those weights that drive how a model transforms its data and therefore how it comes to a final decision. Now, we can reduce the fidelity of this. So if we reduce this to 16 bits floating point, you can see the weight distribution changes slightly, but not altogether that much. But with the space-time trade-off, we've actually saved 50% of the computational power needed to run that model. So suddenly it becomes a lot more viable to run these models on more constrained resource, especially if you have things like IoT devices which can't connect to a network or something and need to perform their computations locally. Something like quantization that doesn't cost 20 grand a GPU may be a viable solution. You can see correctly that has 4-bit quantized weights. You can see here it's a lot different to the actual 32-bit floating weights, but crucially it can actually run on an off-the-shelf £100 computer. The 32-bit weights just physically would never be able to run on that. The 32-bit weights would never be able to run on my laptop, for example. There's a really good library you can utilize to perform this, and we'll go over that now. So what I'm going to do here is transform the original model. First of all, can you see it at the back, or did I zoom in? You all good? Cool. I'm going to transform. This is where having live demos hurts you. This worked earlier. Did I? Ah.
Okay. Ben, do you mind zooming a little bit, mate? Is that all right?
Yep. If I can figure out how, I shall do so. Command plus? Yeah. Thank you, audience participation. Right. So I'm going to take, is that fine now? Cool. I'm going to take these 32-bit weights and I'm going to quantize them down to 16-bit. You can see here what it's doing. If I go up a little bit, you can see the shape and the fundamental data type used to store the weight changes. In this particular instance, from a float 32 in the talks library through to float 16, you can see the shape of each individual matrix there. This will take a few while. So
is it fine if I ask a question about quantization now, or should I?
This is going to take about a minute, so yes. What's your question?
So you mentioned that for audio signals beyond 16-bit, the human ear can't perceive changes. I mean, the changes are quite minuscule. So is there something similar for large language models as well? Because that came to my mind then. Like, do we even need 32-bit quantization, for example? Can we just stick with 4-bit or 8-bit or even 16-bit?
I think, so the question was where I gave, I was going to repeat it for where the example I gave of audio, where going beyond 16 bits of depth, the human ear can't comprehend it, so the space-time trade-off isn't necessarily worth it. The question was, for large language models, is there a similar known cut-off point where the gains aren't worth it? And I think the answer to that ties into Matt's talk, which is the slightly annoying thing about LLMs or LRMs is that they're non-deterministic. So it varies on a use case by use case basis. You will need to perform rigorous internal testing to figure out if quantizing your models is appropriate for your particular use case. Because it is a science, you know, there are fundamental scientific mathematical principles underpinning all of this, but the way that models work, I mean, take reasoning, right? The current generation of models are large reasoning models. They sort of break down problems into reasonable steps like a human. I believe the paper only came out in something like 2019, 2022, where that was discovered as an emergent behaviour in sufficiently complex models. And it's only since we discovered that we've managed to utilise student-teacher models to then instill that behaviour in less complex models. So in terms of is there a known quantization point, no. You will need to figure it out for your particular use case. But in terms of testing, hold that thought, because I have a testing story about that. But you can see, is that good? Does that answer your question?
So what if it's a general kind of applied to many different fields in terms of, it could be tech, it could be health, it could be economics. If it's in different areas across the board, like generic, what would you say?
Right. So the question was, what if the model is more multi-purpose, it's not specialised, it's across multiple areas? I would say go with 16-bit first. It's a reasonable trade-off to sort of half the amount of computational usage, but it really highlights the need for mature, rigorous testing internally to make sure the modules you have are fit for purpose, because ultimately that question isn't a technical one of, oh, do I lose this accuracy here, do I lose it here? It's a question of, is this model fit for purpose? And that's a business question, that's not necessarily a technical question. Like a model that only uses 2-bit weights might be entirely appropriate for your use case if the business context and the business goals align with that. So, yeah,
Can you give examples?
It depends, right? If you're
Could you give some examples?
If you're training a model to do AI code generation, you probably want the full 32-bit of quantization. If you're doing sentiment analysis, then you probably want to, how much can you get away with not necessarily being accurate and not alienating your users, right? If you're doing sentiment analysis to recommend products on Amazon, maybe 8-bit is fine because, you might annoy 4 people out of 10, but the other 6 people still buy your product. So it really depends on the use case, I think.
Okay.
But no worries. But you can see here, it's reduced all those weights from 16-bit to, from 32-bit to 16-bit. We can even reduce it further through to 8-bit. So we can take the original 16-bit quantized model and we can quantize it further to 8. You can see here some general parameters about the model, some of its inputs. You can see the weights here, for example, this is the input, the weights and stuff, and the original size for it was, let's take this one, is reducing it to 8 meg from I think 112, but I'll show that more accurately, there we go, later. So that's now quantized it, and this original model, which was a state-of-the-art model published I think in 2024 using 32-bit floating points, which could only be run on very advanced Google Colab notebooks. The demo gods have been not very kind today. Let me close this one. Right. But here, so this model is a history model. It utilizes a concept called bounded WAG to be specialized model based on the Homeric myths, which if you're not a history nerd like me, those are the Iliad and the Odyssey, some of the oldest texts we have. It's a model intended to assist people with learning about that aspect of history. Priam is a preeminent figure in those myths. If I ask it a question, I get an instantaneous response. On my laptop, I'm not having to spend 20 grand on GPU. I'm just running it on my MacBook. Yes, utilizing 8-bit quantized weights means that the response isn't going to be as accurate as 32 bits, but it's still relatively okay. For context, this model was deployed to AWS with 8-bit quantized weights, leading on from Matt's comments around needing rigorous testing. Experts in Homeric myths, so people with doctorates in that subject, evaluated that model with 50 different questions across a week-long basis, and they found that it generally performed okay. There were some areas it didn't. One thing in particular, it really struggled with narrative causality, and so by that I mean there's an event in the Iliad where Patroclus dies. It's Achilles, well, that's up for debate, but it's a known entity in the Iliad. It put it down as, it consistently said that happened in book 1, it actually happens in book, I think, 9. So there were some space-time trade-offs, but ultimately I was able to quantize the model, deploy it to AWS, run it out my own pocket, and for the grand cost of, I think it was £16 over a week, I had a model deployed to the web with a web interface that experts in that subject could evaluate. And I think that's where that leads on from Matt's point, where a lot of the time people making this, people putting in the mechanisms to utilize this, such as ourselves, will be experts in the technology, but that doesn't mean you're an expert in the subject. If you're making an AI model and the thing which it purports to do is completely outside your subject expertise, I'd personally say there's an ethical onus there to get actual human experts in that subject to come and evaluate the model. But you can see that I got a near instantaneous response. I think, no, okay, I need to Control C out of that. There we go. You can also see that if I can run my own chatbot UI locally on my laptop here. I can ask the same question. It will go away and have a think, although I'm currently blocking the thinking part of my head, so apologies for that. And in a relative bit, because of the overhead of the UI being there and stuff, we will get a response. But there you go. You can see here, it sort of says the behavior model. So what Matt was saying about prompt engineering, this particular AI has different behaviors it can exert, which you can switch between. You can see the model used here, the question and the answer. Something which was state of the art last year, only available for your research papers, I've managed to quantize and run on my laptop and get a response within 10 seconds. I've managed to quantize it and run it on a Raspberry Pi, albeit getting a response in 8 minutes, but still a state-of-the-art model. And the takeaway from this, which I want you to have, is that quantization is a useful technique and it may be pertinent to your use case if you're running your models under constrained compute or on the edge. So there we go. Questions, dramas, llamas, bananas. Tentative claps. There you go. Question?
Actually, it's very interesting because one of the main benefits of running on your own computer is things like, protecting trade secrets, state secrets, privacy, data, anti-surveillance systems. So in terms of stuff like that, it is true that it's getting crazy, right? If you want to on-prem like the very best models, it's crazy. It's like so expensive, isn't it?
Yeah.
To be able to run it on like a server or even hardware. So in terms of the trade-off between obviously the performance versus the costs, where are the industry, from your experience, kind of finding the optimum kind of balance between both?
Cool. So the question started with a preamble around privacy concerns, which are quite on brand and on topic for current AI and ML usage. And the question was around which and do correct me if I'm wrong, which industries could potentially benefit from running stuff?
So what I said, like, what was, like, from your experience in the industry, because obviously the cost versus the performance, obviously everyone would like to have the very best models running on their own physical hardware, but obviously, you know, it does have to be pretty justified to invest, you know, tens of thousands on, you know, the CPUs and the GPUs to be, and the RAM and so on, to have the top spec all across the board to be able to run that. And also, sometimes it's only worth it if it's always being used, because if it's not always being used, then, you know, the depreciation of the hardware also is a big thing. Because next year and 2 years time, that hardware has lost half of the value. So, and also there is the fact that LLMs keep going up in terms of the demand of the hardware. So the question was more like, where do you see the industry finding balance between the cost of the hardware to run it on-prem versus the performance?
Okay, I see. So the question is around the cost-performance trade-off around industries running it on-prem themselves. And what my experience is in industry of where that's going. I've increasingly seen companies wanting to host LLMs and LRMs themselves in order to get around the cost of off-the-shelf SaaS services like Bedrock. I think that with I don't think invention is the right word, but with the advent of MCP servers where you can hook in these models into your own toolings and you can hook them up to your own systems, I think the capabilities and the direction, especially around the hype and the investment, would be that the companies that can afford it would probably want to start running things on-prem and hooking it into their own systems. A good use case would be, one of the clients of mine, I can't say which one or for what use case, but a good example would be they moved away from Bedrock because of the cost, and they instead started running their models on their own Kubernetes clusters to reduce the cost without having that SaaS overhead. So I think, yeah, the direction I've seen is to only for the very large companies that have the money to start bringing it in-house and plugging it into their internal systems. Cool, thank you. Questions? Yes?
See any sort of response time or performance trade-off between using, say, like a 30 billion parameter model that's been quantized down to around the size of like a 7 billion parameter model, and they're basically taking up the same amount of space and memory? Is there one that sort of performs better on certain metrics, or is it variable between model families?
It's a good question. The question was around if you compare, say, a 30 billion parameter and a 7 billion parameter model, and the 30 billion one has been quantized to the point where it has the same computational requirements as the 7 billion one, and correct me if I'm wrong, is there any space-time trade-off between those? Yes is the answer. I think so there's a concept in AI and ML when you're training models around validity and you have concerns like overfitting. If you're taking a larger model and you're quantizing it down, and I haven't seen this, but I would theorize that a larger model that has been quantized down as opposed to one that has initially been trained with fewer parameters may be more susceptible to overfitting because you're taking a high fidelity feature landscape and you're reducing that down. But equally, the lower one, depending on the training data that went into it, if that training data was absolute garbage, then that may also be susceptible to overfitting. It depends on the model by model basis, because really the quality of them, yes, it's in the architectures, yes, it's in how you run them, but it all relies on the data really. So you need to really understand what these models are trained on, and it's a big problem with explainability and usage because a lot of the commercial ones don't share their data sets. So you're only really guessing what they're trained on. You don't actually know, which is a real problem because if I go back to my demo. A really pertinent example would be, I can't remember when it was, maybe 5 years ago, there was a research paper published on it where the training data for a model was for some tech company, I can't remember which one, and it fed it all its CVs, and you're basically going to have an automated AI process to figure out who would be the best candidates. Now, because tech inherently in STEM has inherent bias towards cis white men, right? It found that model inherently reflected that bias in itself because it had learned within these weights and biases here to attribute bias to favour people with names that sounded like cis white men as opposed to basing it on the actual qualifications and expertise of the person. So you need to be really careful about the data. So it's a long way of saying, back to your original question, it depends, if the 30 billion parameter model has had a better data trained on it and you've quantized it down, that's going to be better than the 7 billion one, which has just been fed a load of biased data that it's only going to reflect things you don't want it to. Which is where perhaps Matt's guardrails come in, so tie that in. Cool, all good?
Yeah. Like models on local devices now, they sort of moved more towards getting some large language models to work on mobile devices as well. They're tending to use larger models that are quantized down so they can fit onto the mobile device, or are they sort of tending towards just training these really nano models that can fit onto these devices instead?
So the question was around how models running on mobile devices, whether they're being quantized down or if they're sort of getting more specialist, lower fidelity models. A lot of the big players, your Apples and Microsofts and whatnot, the AI doesn't actually run on here. It's just a interface to interact with the back-end processing happening somewhere in the cloud to then feed the data back through to it. I think there was a talk about 6 months ago around using Open LLM where you might be able to orchestrate that. A lot of the times it's doing that. The only place I've seen quantized models needed are where you can't guarantee network connectivity and you can't have bursty data. So with traditional IoT, when you can have bursty data, you just leave the device there, and whenever it gets some connection, it feeds up all the data and you deal with it. If you have a device that absolutely must act within a set SLA and it can't afford, even if there's a network outage, to not respond to it, then that would be a good use of a quantized model within that specific embedded space there. Cool. Any other questions? Yes. You, and then I'll get to you next.
As I know, first of all, the languages support is reduced from language models to reach the quantization. Maybe do you know how the quantization of image generation models can be reached?
Okay, so the question was around quantization for image models. My honest answer, and it's probably going to upset you, is most of my experience is with natural language processing. So I actually don't, I'm afraid. And I wouldn't want to give you false information. But a lot of my expertise is in natural language processing, sentiment analysis, and named entity recognition, as opposed to image recognition. So, anyways, sorry to disappoint. Yes, question?
Yeah, thanks for a nice talk. I was just curious, could you go into a bit more detail? Because I think I saw that you use like GGML. I think that was the library that does the quantization.
Yeah. So the question.
How it works.
Yeah. So the question was to go into more detail around, in my demo, I utilize a library to quantize the weights, and if I could go into more detail about that. So. So I utilized a two-step process to quantize it. So Llama CPP is a really useful library in the AI/ML space, especially if you're using models which are based on Llama. Their repo contains certain scripts that you can utilize to do conversions between Hugging Face models, and you can transform it to GGUF, and you can then transform the weight from a 32 to a 16. So their repo has an off-the-shelf script that I utilize to do that. However, once that is done, then it becomes a little bit more complex, and they include a make file that has certain target commands to utilize C++ to then further quantize the weights from 16-bit to lower fidelities. The initial conversion is done in Python between 32-bit and 16-bit, but then from lower to then lower fidelities like 16 to 8 or 4 or 2, there's then a make file that is included that has C++ commands to then reduce that fidelity. Does that answer your question?
Yeah, thank you.
Cool. Yes?
Do you have any expectations, like hopes, like when technology will be developed in the future?
The question was, do I have any expectations or hopes about where the technology will be developed in the future? I do. I don't know if they're naive or not. I think there's a lot of investment and time going into it. I think my hope would be that a lot of it would be utilised to make educative environments more accessible. So this particular device here and this model that I made, I done it as part of my undergrad intended to create interactive exhibits in a museum, whereby if you have individuals whom perhaps aren't comfortable interacting with humans, or perhaps they have speech impediments, that if you give them a device such as this to which they can ask their questions, they may become more engaged. There's also studies that were done in Germany with a chatbot called Chim, which was installed in people's phones. They found that by having that sort of interactive interface, that individuals felt a lot more comfortable to ask questions that perhaps, if they focalised, they thought they might feel a bit stupid or silly for asking. There were really interesting studies in the 90s in Japan where museum exhibitions were personalised to people's interests, and so there was a bunch of exhibits taken. They were a bunch of metadata essentially made about them by the curators, the actual experts. An individual would come in, they would select the objects they're interested in, and then based on a similarity factor index, though it wasn't called that at the time, the exhibition would then suggest to them other things that they're interested in and build the space in 2D. That was limited by the tech of the time because it was just on like a really clunky LCD display in Japan in the back room of a museum. But regardless of anything else happening, my hope at least would be that there's a lot of ongoing research in the museum and educative sectors. I would hope that alongside, for example, the British Museum done a multi-sensory pack for people who perhaps are hard of vision or hard of hearing. I would hope it would get used alongside that to perhaps open up public spaces. Anything else? Though you're looking quite stern, so it might be the last one. Okay, thank you.